function of GA proportions whenever you take a function by the group G and its maximum force. So that's essentially it. Yeah, it's a different type of story, right? Yeah, so it's, that's right. So there is I should mention that there is a different type of methods which uses cluster maps and and in this case this is so for me the background would be just a standard, so I'm going to take X to be a non-similar projective right, it can be also a space. And G is going to be reductive acting on G, and I'm going to make a choose of polarization L representing here. So the stable locus is just given by these 4 points for which we can set these points by a section that is equivalent of a power of polarization, and so that point is matched. So for me, the GA quotient is just going to be the quotient stack of this stable locus by G, in the sense of that this is going to be a 3-moment stack. In most of the cases, I'm going to just use a semi-stable equal to stable. And then there is a symplectic construction of this map just by making a choice of an embedding, of the product polarization yields embedding. And then I'm going to assume that you choose a map for this particular action. Here K, my K that present there is just going to be the maximal compact in the and is not equal to the slides have a tiny bit of mistake, so please allow me to correct them on the fly. So this should be embedded in there. So G, the maximal compact of G maps into the unitary group. And so the moment map of the breakthrough space is just given by that, and so what you do is just take it back to X to the representation that you have. And then by a theorem of Kempf-Ness, the symplectic construction on the algebraic construction are the same. And therefore, I'm going to be jumping from symplectic methods to algebraic methods. So the theorem of P1, the construction of P1 says that there is a surjective map in general that goes from the quadratic homology of X into, for me the quadratic homology is just the homology of the quotient stack X mod G into the homology of the GAT quotient, but this is just induced by this stable, the inclusion of this stable. So the first theorem that I want to present, and actually one of the reasons I want to be detailed in this case, I want to say it instead, it's because I want to quantize this formula. So let's suppose that you have now two choices of polarization, so you can actually form two different quotients, right? So a positive and a negative quotient. And so you would like to relate first a mapping that goes from the quadratic homology to the first quotient, and then integration of those classes into, this is what I just trace. This is just integration of those classes. And then with respect to a different choice of polarization. So this formula that Kaplan introduced is essentially tells you what the relation of these two compositions is if you go from one way to another. And the formula states that this diagram does not commute, but it does commute, well, it doesn't commute, but it commutes up to certain contributions of classes that some correction terms that are given by contributions coming from fixed point components of one parameter groups. Okay? So more or less the story goes as follows. So you can form the moduli space, the master space, and this construction is due to Tadeusz, the one that I actually described here. So this master space will be essentially parameterizing all possible quotients that you can get that go from L minus to L. Okay? So if you take the parameterization of this line, then you can actually, this inherits an action, sister action, and then you can just take quotient with respect to the parameter T that comes from the action of the sister action of ions. Okay, the contributions that come in here are given just by looking at the fixed point components of one parameter subgroups. In this case, I am just picking an element in the algebra. And then looking at the system stable locus of this. So this is, for some values of t, not all values of t. Generically, these values will not contribute, but some of them will be fixed by one parameter subgroups, and those are the ones that will contribute to the non-competitive this diagram. So in this case, the action that is generated by this one parameter group acts trivially on the fixed point component, and then what one can do is just take the integral. So this map that I'm using here, this tab, which is what I call the localized trace, or the fixed point trace, will be just integration with respect to a small moduli space. This, the contribution from the fixed point locus, by restriction to the fixed point component, and then twisting by the avoided class of the normal envelope of the fixed point set. Okay, so this is actually more or less what is done. So in other words, and then taking the residue, because this originally maps into the equivalent homology with respect to the sister action. So if you take the residue, it means the coefficient that corresponds to psi minus 1 or psi, in this case is the equivalent parameter, then it will give you a rational number, and then this is what this formula states. Okay, so any questions about that? So this is a very classic formula. The way of proving it is by using localization of the mass express. Standard localization. Okay, so the organization for the homology is just what you look at the variance, the wide variance of the equivalent homology with respect to the maximum torus, and then that reproduces entirely the usual equivalent homology. So there is a bundle that is associated with this diagram. So it's a lot easier just to look at this picture, this symplectic setup. And this is essentially measuring the x's whenever you look at the two different quotients. So if you take the abelian quotient to this side, so this bundle will be essentially that one, and then the x's will be the k of t represented. So this is what I have on this bundle, so the normal g of t bundle. And then Martin's formula around 2000, and actually this is a very curious detail. I think this is the first paper in the archive of the millennium. I am not sure. Yeah, so it's actually something like 2000 and then 0001 and 2. So it's probably people waiting there, the turn of the millennium for this data. But anyway, so this formula is actually very easy to state. In this case, this formula claims that there is a commutativity diagram of, if you look at the restriction map that goes from the standard equivalent homology, the non-ability case, and the bigger case. I assume that these are isomorphic. And then you take the Human map, and then if you do the same thing, and then you take the trace, so you take iteration in this way. So the only thing that you have to do to the trace is just twist it by the order class of these x's for the quotient, and divide by the because there is a repetition by the way. So there is a repetition of that, and so the formula reads very simply like this. So if you take Human map, and then you take the trace, meaning integration, it's given in terms of the abelian pages by certain the classes, take the Human map, and then take the integration with twisting coefficients. So this is actually very natural. So more generally, he actually describes Martin describes a map that is from the correct model T, whose kernel is essentially the idea of given by the order class. So the example that that I am going to be referring to is essentially, whenever you look at the Grassmannians, and then you look at the standard quotient of the Grassmannians is well, the non-abelian quotient is the Grassmannians, but the abelian quotient would be a proper for previous stress. Proper choice of sections. So with the localization, so I have already described too, so block crossing, localization, and then with the localization is the following diagram. And so the idea of this is what would happen if I want to describe this trace, the trace of this integration of equivalent classes of the GIT quotient in terms entirely of equivalent homology. And we can describe the following formula that says, well, if you want to understand this, they do not commute these two. The error comes from contributions of one parameter group, so actually points of the non-square normal map. This is very, very difficult to describe in general. Actually, in Newton's paper, there are lots of things that I didn't bring up this one, but I'm going to avoid it, and I'm just going to tell you what happens in the multi-product case. So the model of today is that all these three formulas actually hold. So with the localization, wall crossing, and organization, they will work in the quantum world, and I'm going to talk about that is not classical quantization, but quantum model. So of T, the diagram of the modularized spaces of stable maps, target X, he just constructed a product, which I'm going to call it a product A times B, shifted by a class, and it's just given by this from our students at the first time. And the cohomology of the quotient will be replaced. So the formulas that I have above, right? So I have the query cohomology and I have the cohomology of the quotient. So for most of the cases, it's just going to be the stacky cohomology of the quotient. But for today, I want to avoid that, and I'm just going to assume that this quotient is smooth, and then it's just a standard cohomology. So all of this is pretty well known. The quantization of the Q1 map, so that's the first thing to check. This construction is actually to this Woodward, and in order to get a map that goes from, by the way, I made there's a typo there, this should be Q, or this should be Q there. So to get the quantization of that map, one actually counts representable morphisms that go from the standard orbital Q1 up. Okay, so this has an orbital singularity, a static singularity at infinity, and it maps into the quotient stack x mod g. But in a way, so that the condition that he imposes is that the static point actually maps into the semi-stable locus. Okay, and in that way, he studies these modularized spaces, and then he quantizes the map, and then what he obtains is the mathematical map. I will not write the formula, and I will not describe it today, because this will appear as a limiting in a limiting situation. So I'm just going to tell how it is a picture, but I am not going to do the analysis. This is just to tell you more or less what happens. So the quantization of the traces, so the classical trace I already said that is actually an integral, right? So in the quantization of the traces, it was already suggested by Leontal in these early papers that the proper quantization should be the graph potential. And this graph potential are just parameterized maps of by degree 1, comma d. Okay, so those are graphs. So by the way, this should say something like the E cross X So sorry, it has so many typos. I actually corrected these typos yesterday when my computer crashed. So this is a backup copy of the book. So sorry about that. But anyway, so so far I already told you that these formulas hold, and then what I have to do for quantization of Q1 But all the other potentials, including all the other quantizations for all the other terms in the formulas that I wrote, they need a tiny bit more work, and this essentially would gauge potentials come into place. So I'm going to tell you what that is. So to quantize the all contributions, I'm going to use the modularized space of gauge maps. Okay, so for that, I'm just going to tell you what that is. So in other words, you want to study proper variables of say maps that go from a curve into your quotient. So to start with that, so for me today, I'm going to fix a curve because I am using the graph, the modularized space of graphs. So it has a fixed component in there. So I'm going to look at the fact that x mod g is actually just a proper substack of x mod g, and therefore every map that goes from C to that is just like standard definitions. It's just going to be composed of a principal component and then a covariant map that goes from the T model to n to x. That's equivalent to say that this is just a section of the associated model where I take the P cross x, so I just apply that, and then I apply that through G, and then that's essentially it. So, however, this is of course not going to be a good modularized space. So what I need to do is impose more conditions on that semi-symmetric condition. So the first thing that I have to do is to compactify, and the way I compactify it is by allowing rational bubbles to appear. So that's essentially just thinking of stable maps that go from a null curve with a fixed component, which is C cross x mod g, right? So, and the degree that I am going to request is 1D. This degree now is a covariant degree. Of course, so you are replacing the standard homomorphic theory by a covariant block. So this is what happens. So in particular, this modularized space is actually quite large. So it will contain the modularized semi-stable models, for instance, G models of the C, and the moduli of stable maps as well. So it's a very large modularized space. So the semesterability condition, since I am working with pairs, so I have a principal bundle and I also have a map, it's naturally a composition of two different semesterability conditions. So the semesterability condition for bundles was already described by Ramanathan, and it goes as follows. So you take a parabolic subgroup and a parabolic reduction of the bundle you have here. And so you look at the one-parameter subgroup of the parabolic. And then by that, well, that is essentially given by a choice of weight. Okay? So this is how it is described. And then I will take an associated bundle, which is a deformation of the real one that I have, and then I will look at the bundle by attaching here again, by twisting with this weight that I have, these one parameters. So what I do is I take a limit as z goes to 0. This is essentially like in finite dimensional cases, whenever you take, you want to analyze the stability of the point, of course, for polarization. So you take a one-parameter group, and then you flow to 0. And then at 0, that's a limit, right? So then that can be considered like the graded point in that case. So the Ramanathan weight is just the degree of the associated bundle of the graded by twisting, well, this is a line bundle, so it's a representation of the lambda. And I assume that lambda is dominant, so that all of this makes sense and actually exists. And then P is stable, actually, sorry, semi-stable if there's an inequality here. Okay, so this is actually smaller, bigger than 0. So since I have a section as well, you can also change the definition of the section by taking the action of the one-parameter subgroup as well. And that will define a section of that bundle, the associated bundle that I take. And then as z goes towards 0, the map will actually non-converge to something. So it will be a stable map. And then in that case, this is what I call the graded view. And this would be a map that is line, it's a section of the bundle that I have also the graded. And then the property that this has is that all its values that it takes is actually on the fixed point of the one-parameter that I have. And so certainly I can just take the weight of this distraction, the induced action of the polarization at that particular point set. And this is a generic convoluted. This is a very convoluted type of definition for the degree. So one of the way that one can do it is by introducing the moment map, and then this definition of degree would be the same as taking the value of the graded, with the value of the moment map of the graded, pair it with the one parameter, with the weight that I have, and then that gives you a number. So you just integrate the version of that, and the volume formula goes in here, and then that gives you a good notion of degree. And then we say that the pair P, U, that is an element of the quotient stack, would be semi-stable if only if the sum of the two degrees are in there. This is more variable. Let's do an example. This example has two types as well, that I corrected yesterday. Let me actually tell how it goes. So to understand very well these modularized spaces, let me consider the applying space here and then a sister action in it. So I'm going to fix a bundle of degree T, and I'm going to take the genus 0 here. So I'm going to assume that this is P1. So in this case, the parabolic is itself, so that the reduction is trivial, and then I'm going to take lambda to be an element in the lattice. So it's an integer. And then the moment map that I am choosing for this action is going to be just given by the standard moment map that you have to the grade of the space, just like that. So the gradient of P is itself, there is nothing there, nothing new. And then the gradient of U is just going to be the limit of this particular point. This is very easy to do. Since C elements are fine, there are no wobbling happening, and so it's going to be an honest limit. So just very quickly, this only would exist if, for instance, this is strictly positive. I made a mistake there. Okay, so it doesn't exist if this is positive. The gradient of U would be 0 if I'm only for all lambda, right? So if U is exactly 0, and gradient of U would be 0 if U is different from 0. This is strictly smaller. That's it. So these are the conditions. So notice that I made a mistake in that. And so the weight can be computed as follows. So you just take the pairing of the degree with the lambda that you have, and then the integral, as I said before, the moment map. The moment map at 0, if you notice, is just 1. But so that's the only thing that we have. And then we have the lambda, so it's lambda integrated with the volume of C. And we can assume that the volume is equal to 1. So this is one of the starting points whenever we did this computation, that actually we started plotting this variation of polarization as area dependence, and this is because of the volume turned out this way. So that is in this case. And so the map, okay, so is going to be semi-stable if mu m is simply smaller than 0, and for u equal to 0, and unstable if lambda is greater than 0 and mu is exactly equal to 0. So in this case, the moduli space of the semi-stable maps that go from P1 to Cm to 3Z is just a projective space, just as we expect. In the third case, it's exactly the same situation. You just have to take a bunch of weights, and then there's an instability condition. If, for instance, the polarization is really large, it will be completely dominated by the multiple weight. And then something will be semi-stable, and only the U mounting is semi-stable. Okay. So the first theorem is that those moduli spaces have a perfect construction theory, so you actually are allowed to take integration. And so you have formed the gauge potential. So this is the quantization of the traces that I was talking about. So that's just by the standard formulas. You just integrate the moduli spaces. You pull back to the classes in classes, and then you introduce an exponential term. And then the theorem that we have, the first theorem that I proved with Chris was that for any two traces of polarization, then you can compare the two traces. The traces go from positive to negative. These are gauge potentials, by the way. It's just given by very explicit formulas on the fixed point components. So the fixed point components in this case are just gauge maps that will map into the portion. So the physical portion, the portion that has the fixed curve P1 will map into the, by the way, C is P1. I mean. So it will map into the fixed point components, and then everything that happens to the bubbles, they are free to go onto C. So that's exactly fine. And they are twisted, just as in the case for the ball crossing formula that we have, they are twisted by an index bundle that is given by the normal bundles of the fixed point components. So one of the things that I forgot to mention with this is that with this formula you can actually prove the Greta conjecture of 1 as well, just by noticing that, for instance, if the weights on the fixed point components are of a certain type, meaning that if the covariant weights add to 0, in all the fixed point components, then I actually can show that this term vanishes up to, well, not vanishes, but it's actually a delta function supported at one point, and therefore that tells you that the potential on one side and the potential on the other side are essentially the same, and then that proves the Greta conjectures for duality type in this case. But that's not the topic today. So the appearance of the quantum P1 map is as follows. So if I take now the two polarizations, there's a cascading of one or another. That's essentially like making the curve large or small, as I was saying before. Then as the delta goes towards infinity, then the theorem of Woodward says that this diagram commutes. So you can think there is a map that will fill this this triangle. So meaning that they take a trace, the covariant trace, the gauge trace, taking the standard graph potential from here to there. So that this map will yield a factorization of the gauge trace. So this map actually appears because the moduli spaces at the limit is not the same as the moduli space of maps to the quotients. So there is some behavior, weird behavior happening. And for the people on those, well, this is a mirror symmetry conference, so what people should be thinking of this diagram is essentially in the two cases as follows. Is, by Givental's version of mirror symmetry, the gauge potential is that function. The graph potential is J function, that's a fundamental solution to the quantum differential operations. And then the mirror transformation is the one that makes them equal after all. Okay, so, and in this case, we are not using anything with this span or any other condition. The problem is that to understand what this map is actually absolutely different. Actually, Chris has promised me a couple of more computations that we have been able to do so. But anyway, so this is the whole idea, and then you can actually record the I and the J functions if you localize with respect to the sister action of P1, just as in the Givental's case. So then there is another limit. So we already told you what happens when delta goes to towards infinity, so that's the large limits that we map into the quotient. So if delta is actually small, the bundle trivializes. So the only thing that you have, so since this has to be semi-stable, the bundle is just trivial, and then again I made a tiny statement here. So this has to be p cross x, and the degree has to be e. So these are graphs. And then the action of t in this modularized space is just by the closure position. And then this is an actual GIT quotient. So what we are trying to say is that if you actually take the limit of the polarization when the polarization is very small, what you obtain is a GIT quotient. And then we're in the classical picture as well. Okay, so the modularized spaces are not difficult, they're actually very simple, and that's why the I function is always combinatorial, in the same as this case. So everything is absolutely computable in the small limit chamber. So I guess that the moral of this is that if you want to prove anything, prove it in the small chamber, then try to bring it to the large chamber in some sense. So this is the quantum version of the with trace. So it's essentially integration of classes with respect to this modularized space. Okay, so then that gives us the proper quantization of this modularized space. And this is a graph. So the theorem now reads as follows. So this is the quantized version of the Witten localization. It says that you can actually compute that if you want to compute this, by the way, that should be another break. It's not. So if you want to compute the trace, okay, the gauge trace, the small limit, it doesn't factorize just as in the standard case of Witten, but it factorizes with respect to contributions of a very specific terms that appear in the gauge, in the fixed point gauge for one parameter. So actually everything is explicit. So the proof of organization, as I was telling you before, it should be as follows. So now I know if I take the quotient with respect to t and the quotient with respect to t, I will have the two Witten localizations in this way. Okay, so those two formulas are valid. I didn't tell you that everything that I said can be proved if you twist the integration by certain classes. So every single time that I write potentials that contain t, then it's just twisted by the Euler class of the index bundle that takes bundle that represent. And so in the small limit, both moduli are GIT quotients essentially. So that the integrals are then replaced by virtual integrals. And then we have this formula that we're presenting here. But this term is just remapping the coefficients that are the number of coefficients that are with respect to t and mapping it to t. Okay. And then carefully noticing that every single thing that happens from one pole to another one will be carry natural. So this equation actually carries naturally as you look across it. That's pretty much the story. And so then the formula that is the realization of quantum differential equations can be read as follows. So we localize the potentials and we get the I and the J functions, so the equivalent of those definitions. And then what I have is a composition of the quantum map, the localized potential of the quotient x and t, and then I can completely express these two in terms of the abelian multipliers. And so again, what I have to do is just restrict classes as the incoming go. So if I have a class that is G equivariant, I change it to T equivariant, and then I compose the quantum map, and then I apply the potential with respect to the abelian quotient, and then I do the same thing backwards. And then that's how it goes. So let's do an example. Now I know there's some variable that's going fast. Okay, slow down a tiny bit. So let's go back to our example of the Grassmannians, right? So for the Grassmannians, I already said that you can express the Grassmannian as a J quotient, just by taking the quotient by DLR. And then you take the maximal torus, and then you take the equivalent monoid with respect to that. So that's just theta 1, theta r. So those are the generators with respect to the big torus. And then the first term class that appears in here is nothing but the same as the selected class. So this is called monotone in our theory. And in that case, so every single time that you have monotonicity, the quantum Q1 map is essentially trivial. I shouldn't say trivial. It becomes a classical Q1 map. So there are no actual quantum corrections. So it's trivial on H2 of the equivalent homology degree 2. So that means that the only thing that is going on is the classical Q1 map, and there is no other contributions of quantized contributions. So you should worry about that. And then, so you can just ignore it, essentially, the quantum contributions. And then I already told you that in this toric case, because the ability quotient is actually a toric variety, so these do agree on the nose with the given Lie function for the product of free spaces. So we know how to do that, right? So we have this function. This is just the I function of the product of free spaces. So it has a very explicit combinatorial description given by that, where this term that present here is the geometric series that gives the price. So it's actually pretty explicit. The H bar parameter that present here is because I am localizing everything, right? So I am localizing with respect to the fixed points of the C star action by rotating the P1, which is the domain of the curves, right? So the H bar is just that equivalent parameter, and it is the same one as the given description, so you should worry about that. And then that proves that this formula, so this formula is just the analogous of what Ori and Baha wrote in the paper, and then in this case it's just a different proof, and as I was pointed out before, there are many other proofs of the same techniques, and so in this case I just have that. And I think I have 5 minutes. What's next? I suppose. What's next, right? So far the only thing that we have is this idealization. We proved already, as I was saying before, the whole crossing we already proved the Grepland conjecture when the Grepland transformations are GIT type using the whole crossing formulas. But we will really want to bring the same ideas and same techniques, but in the case of hypersurfaces. So for instance, for the green, we can try to see how to extend the results in that case. Unfortunately, we have to deal with fields and so forth, and well, for the people that knows what P fields are. And but we're working on that. We hope that in the next year we have at least a couple of papers in that direction. But we don't know yet how to deal with the perfect distortion theories in those cases. We don't know. Another thing that I want to mention is that the quantum Q1 map, whenever we did the computation of the quantum homology of toric orbifolds, we were essentially using the quantum Q1 map is surjective. There is no really an intelligent answer to why it is surjective, other than we computed directly and we saw that it hits every single generator in the crystal sectors. So we don't really have any good answer for why it should be surjective in general. So the toric case it works, and then that's why you can compute the quantum homology in that case. So another thing that we want to do is to actually prove that the quantum Q1 map is always surjective, and then that will give you a way of computing the quantum homology of all GIT quotients for any G reductive in terms of the quantum homology. How to do that is perhaps just following Q1's idea of studying the certification of the null cone and then see what happens in that case. But we don't have progress, complete progress in that. I think, unfortunately, I also went.
Time for questions and discussion. Any questions? So, let me see if the statement I understood of this lecture of the one, in what case it's true. So, you have, well, in what case you measure first. It is a restriction on the Grepland transformation that you have, or what is it?
Okay, so what I guess what I'm saying, I'm going to call a Grepland GIT transformation if it comes from a wall crossing.
Okay.
So that means but in many cases you can actually do a zigzag type of thing, right? So I suppose for Mori dream spaces you can always do that. So things will factor through wall crossing, and then so in that case the condition is as follows. So if your transformation would factor through GIT wall crossing transformations, and in such a way that at the wall all the normal weights, so the weights, like the normal bundle, the fixed point components add up to 0. That's what I will call current. And then I claim that the two potentials in both sides will always agree up to some delta function. So, in numerical terms, it would be like a delta function, supported at that point. So that is the actual statement. So we'll actually, we have a proof and we know how to do it. So the problem is, well, how you can do it in general. Right? So